Most planets keep their deepest secrets hidden far within them. For a long time, we thought we had solved the secret of Jupiter. We believed there could only be two answers. Either it had a solid, rocky core holding the entire planet together, or it had no core at all, just endless quiet layers of gas. But then, a spacecraft got close enough to peek beneath its clouds, and what it measured did not match either of those answers. It found something much stranger, something no one had even imagined, and that single discovery changed forever how we look at the giant planets. The largest planet in our solar system, which we have observed for centuries, is actually not what we always thought it to be on the inside. And the most astonishing part is that after the secret of this one planet's heart was revealed, we had to rewrite our understanding of planets across the entire galaxy. The name of that spacecraft was Juno. Today, we will drift through the whole story from beginning to end, exploring what it found in the heart of Jupiter that shook the very rules of planetary science. Let us gently dive in. For many years of space exploration, Jupiter's interior was like a blank canvas, one that scientists filled more with theory than with observation. We could observe its storms, its stripes, and its moons through telescopes. But what was hidden beneath those clouds was merely a guess. There were two major thoughts behind this guess. Two ways of thinking, each with its own logic, and each with quiet flaws that no one could resolve. The first thought suggested that Jupiter was formed from a gravitational collapse. Picture the beginning of our solar system. There was a massive cloud of gas, and in one part of that cloud, hydrogen and helium became so dense that gravity began pulling them inward, just like water swirling slowly down a funnel. Then, this process accelerated on its own, pulling in more gas until a planet was formed that was more than 300 times heavier than our Earth. If this were true, Jupiter wouldn't have needed any solid seed at all. Its entire structure would just be layers of gas and liquid hydrogen accumulating endlessly toward the center. In a way, Jupiter would be a star that never managed to ignite, a quiet, failed star with no heart. But there was a lingering puzzle with this idea. If Jupiter were formed only through gravitational collapse, it should have been almost entirely composed of just hydrogen and helium, and nothing else. But every time scientists studied closely, whether through Earth's telescopes or spacecraft sent there, they found heavy elements. Carbon, nitrogen, oxygen, even some rare gases, present in surprising quantities. These things shouldn't have existed in a planet made only of gas. So, if the first thought was correct, where did all these heavy elements come from? This is where the second thought emerged, called core accretion. This idea works much like how small planets are formed. First, particles of dust and ice stick together to form rocks. Then, those rocks collide to create larger chunks. Over millions of years, so much material accumulates that a solid center is formed, perhaps 10 times larger than our Earth. Once this rocky seed is formed, its gravity becomes so powerful that it pulls in all the surrounding hydrogen and helium. The gas accumulates rapidly upon it, expanding gently, like a balloon filling with air, to become the giant planet we see today. And this thought solved the heavy elements puzzle quite easily. That solid core would explain where all the metals and ice came from. For a long time, this second thought seemed stronger. But even in this, some questions remained. Just how big was that core? Was it a dense sphere of rock and ice buried under hundreds of kilometers of a layer of hydrogen that had turned into metal? And the biggest question, could such a solid core survive for billions of years under that terrifying pressure? A pressure that turns hydrogen into liquid metal. And here, the whole story paused. By the end of the 20th century, we had more data, but no clear answer. Pioneer and Voyager gave us our first close-up glimpses. They measured Jupiter's magnetic field and radiation belts. Then came the Galileo spacecraft, which arrived in 1990 and actually dropped a probe directly into Jupiter's atmosphere. That probe confirmed that external elements were present and hinted that the interior was filled with much more metal than just pure hydrogen-helium shells. But Galileo's instruments could only reach the outer layers. Its deep interior remained unsolved. Its heart was still hidden in the dark. Because of this, both thoughts, the collapse theory and the accretion theory, remained alive. Neither could be proven. And this stillness wasn't just about Jupiter. It determined how we understand giant planets, wherever they may be. Because if Jupiter didn't have a core, gas giants could perhaps have formed almost instantly by collapsing directly from gas clouds. But if it did have a core, then perhaps this process was slower, starting with rock and ice first, and then slowly swelling into gas. This answer mattered for the thousands of exoplanets that scientists would go on to discover in the coming years. To solve this question once and for all, scientists needed a way to see through those storms and directly measure the distribution of material inside Jupiter. There was only one way to do this: to measure its gravitational field with more precision than any mission had ever achieved before. And that is why NASA created Juno. Unlike all the missions that came before it, Juno was not built merely to capture images or measure magnetic fields. It was built for a specific, quiet purpose: to fly very close, to skim the tops of the clouds, and to capture even the smallest tug of Jupiter's gravity. By observing where the spacecraft sped up slightly and where it slowed down, scientists could reconstruct how the material inside is distributed. This was finally a way to move beyond mere guesswork. When Juno arrived in 2016 and began its close orbits, the expectation was very straightforward. They just had to find out which of the two ideas was correct. Either Jupiter has no core, or it has a solid core. But the universe rarely gives straight answers. The first results, arriving in 2017, were far stranger than either theory had predicted. Jupiter hadn't formed the way the neat models we had imagined suggested. It was hiding something completely unique inside itself. When Juno's data arrived, it didn't fit into any old way of thinking. Jupiter had neither a sharp, solid rocky center holding it together, nor was it just an endless column of gas. Instead, the spacecraft was painting a picture of a planet whose core was fuzzy, diffuse. Scientists called it a fuzzy core, or a dilute core. This meant that heavy elements were spread out over a very large area, gradually dissolving into the surrounding hydrogen and helium, instead of sitting in the middle like a dense sphere. Consider this. If you place a spoonful of sugar into a glass of water and leave it still, the sugar settles at the bottom like a clear heap. That is the old solid core. But if you stir it just halfway, the sugar neither fully dissolves nor fully settles. It just spreads out hazily throughout the water. This is Jupiter's fuzzy core. Its heavy material is there, but not in one place. Instead, it is hazily scattered across half the planet. There is no clear boundary where the rock ends and the gas begins. And this discovery raised a direct but very difficult question. How does such a structure even form? Planets shouldn't be fuzzy on the inside. All the old theories expected a clear transition, a sharp border, between a dense center and a light exterior. Juno's data was demanding an entirely new explanation. The first idea that came to scientists' minds was a giant impact, a massive collision. This idea was similar to the collision that formed Earth's moon. Collisions between large objects were common in the early solar system. So perhaps, when Jupiter was still young and growing, it collided with another protoplanet, perhaps an object 10 or 20 times heavier than Earth. The energy from such a collision could shatter an once dense core, scattering heavy elements outward and mixing them into the surrounding layers. In theory, this was a dramatic but elegant answer. But since every theory must undergo testing, scientists use supercomputers to run thousands of simulations of collisions between a proto-Jupiter and large objects of different sizes, angles, and speeds. The result was always the same. The collision would indeed shake the core and disturb the interior, but not forever. Over time, gravity would pull the heavy material back down, and it would gather into a dense center once again. Instead of creating a lasting fuzzy structure, the simulations showed that Jupiter would eventually return to a state with a solid core. Recently, researchers published the results of new supercomputer simulations. They simulated those same massive collisions from Jupiter's early history, and every time, the heavy elements that were scattered outward did not stay that way. Over time, they settled back down and formed a dense core once again. Their conclusion was clear. A single giant impact cannot explain Juno's fuzzy core, so this theory was gently set aside. So, what was the real answer? And this is where the story takes its most interesting turn. Scientists' attention shifted from the collision to the birth of Jupiter. Perhaps this fuzziness didn't come from a catastrophe, but from the very way it was formed. In this new line of thinking, as Jupiter was accumulating material, heavy elements didn't just sink and settle in one place. Instead, they partially dissolved into the surrounding hydrogen and helium. Rather than having a clear core and a distinct outer layer, the planet developed gradients, regions where the composition of material changes gradually. Metal-rich at the center, and lighter gas towards the outside. This process left behind a fuzzy interior without any sharp boundaries. But there was another crucial factor: convection. This is the process that usually keeps a planet's interior well mixed. On our Earth, convection constantly stirs the mantle, spreading heat and mixing material. If Jupiter's entire interior were undergoing convection, all these gradients would eventually disappear, leaving behind a uniform structure. However, Juno's data suggests that large portions of Jupiter are non-convective. In other words, they don't mix. And this very stability keeps the gradients of those heavy elements intact for billions of years, instead of them dissolving into a uniform mass. Because of this, the fuzzy core began to look less like a unique puzzle and more like a natural consequence. Jupiter perhaps started with a solid core that never truly became dense. Over time, heavy elements became blurred toward the outside, mixing into the lighter gases, and the overall lack of convection maintained that fuzzy state. What Juno showed was not a planet broken by a catastrophe, but a planet whose interior was formed in a way completely different from the neat models we had always imagined. But now, one big question remained. Was Jupiter just a lone, strange case, or is a fuzzy core a common characteristic of large planets? To find the answer, all eyes turned toward the other giant of our solar system, Saturn. And we were fortunate to have a spacecraft there at the exact right time, Cassini. But there was a challenge here. Cassini had not dived into Saturn the way Juno had dived into Jupiter. So, to peer inside, scientists used an incredibly beautiful and clever method. They turned Saturn's rings into a seismograph. Now understand how this works. Just as we use earthquake waves on Earth to map the interior of our planet, vibrations also rise within Saturn. And when Saturn vibrates, its gravitational field shifts slightly. This slight movement creates tiny waves in its rings. So, those rings that look merely beautiful to us are actually a record of the planet's internal heartbeat. And the story of this idea is also amazing. This thought first occurred in the 1990s to two scientists, Mark Marley and Carolyn Porco, who realized that Saturn's vibrations could create waves in its rings. Then, in 2013, Matt Hedman and Phil Nicholson actually observed these waves in Cassini's data for the first time. Later, Christopher Mankiewicz and Jim Fuller conducted a deep analysis of these waves. Fuller said something very lovely. He said, "Saturn is always trembling, just very gently." This technique even got a name, chronoseismology. This name comes from the Greek word chronos, which is the Greek name for Saturn, meaning the study of Saturn's internal waves. And when scientists combined this ring data from Cassini with gravity measurements, a clear picture began to emerge. Saturn, too, did not have a sharp, solid core. Instead, it had the same thing inside, the same gradient, heavy elements, more concentrated toward the center, but spreading gradually outward without any clear edge. In other words, Saturn also had a fuzzy core that extended up to nearly 60% of its volume, filled with ice and rock 17 times heavier than Earth. And this was a turning point. If both Jupiter and Saturn share this same characteristic, then it is no longer likely to be the result of some rare or random collision. It means that a fuzzy core is a natural consequence of the formation of large planets. Instead of being a strange exception, perhaps it is the rule. And this doesn't stop with just our solar system. We have discovered thousands of exoplanets, many of which are gas giants, even larger than Jupiter and Saturn. If this fuzziness is a fundamental part of how these planets grow, then the neat, layered models we have relied on for decades might prove to be very simplistic. It is possible that across the entire galaxy, gas giants do not have distinct cores and outer layers at all, but rather a fuzzy, mixed interior. But there is one more secret in this entire story that is perhaps the most perplexing. Jupiter's magnetic field. It is the most powerful of any planet in our solar system, so massive that its tail extends past the orbit of Saturn. We expected that because Jupiter rotates so quickly, its field would have a neat, balanced shape. But Juno showed that this is not the case at all. Jupiter's magnetic field is lopsided. It is powerful in some places, and somewhere weak, completely unbalanced between the northern and southern hemispheres. It has strange patches of intense magnetism. There are even more than one south pole. On our Earth, the magnetic field is formed by the movement of molten iron in a clear system, but on Jupiter, it is metallic hydrogen that does the job. Hydrogen that is under so much pressure that it flows like liquid metal. It should have formed a clear field, but it didn't. Scientists hoped that perhaps the discovery of a fuzzy core would resolve these strange anomalies. But the opposite happened. When they put the fuzzy core into the model, it matched Jupiter's actual field even less. A new idea is that perhaps it rains helium there. That is, helium droplets separate from the hydrogen and fall downwards, much like oil droplets separate in water. And perhaps this is what makes that field so strange. But the truth is, the fuzzy core didn't solve this puzzle. It made it even deeper. We thought we had solved the secret of Jupiter's heart, believing there could only be two answers. Now we know that the truth turned out to be far stranger than both those answers. Neither a solid core nor an empty belly, but a blurry, fuzzy secret that extends halfway through the planet. And as soon as we found an answer to one question, it raised 10 new ones. Saturn repeated the same story, and perhaps countless planets in distant galaxies are telling the same tale. And perhaps that is the most beautiful thing about this science. Juno, which took its final breath in September 2025, as it gently dove into Jupiter's atmosphere, spent its final years teaching us that the planets we have lived alongside for centuries can still surprise us today. With every answer, Jupiter poses new questions, and perhaps that is the very thing that keeps pushing science forward. The universe is vast, quiet, and full of mysteries waiting to be uncovered in the dark. Rest well, and let the quiet wonders of the cosmos carry you into sleep.